So two halves. My talk will be on two halves, one on sampling, the other one on chemical shift. In sampling, we'll be covering up about the NMR tubes, labeling the NMR tubes, and then solvent solubility and quantity. Cleanliness, filtration of the sample, then contamination, followed by solid state NMR samples, and then deuterated solvents. So the sampling techniques, first the NMR tubes and caps. You can see the pictures here. These are all some of the NMR tubes and with its caps. So these are all the caps which are shown down. So they are typically made up of borosilicate glass. They are around 7 to 8 inches in length and 5 millimeter the tube diameter. And the most common one which we are using is 5 millimeter, but there are 3 millimeter and 10 millimeters are available. In particular, if you go for boron-11 NMR, so we switch to quartz NMR tubes. Because in borosilicate glasses, you know, there are borates present, so it will be interfering in your NMR spectrum. So if you go for boron-11 NMR, we use quartz NMR tubes. It is very important to see that the tubes are uniformly thick and it should be well balanced so that the NMR tube spins at a regular rate. It will not be wobbling here and there. Usually about 20 hertz in the NMR spectrometer. For 300 to 500 NMR tubes, we have Wilmad 528, and then from Aldrich, and then from Norrell, and from Nord's grade. For boron NMR, we have Wilmad 528 PP quartz tubes are available in the market for these NMR tubes and caps. This is another important thing is the labeling. So when you take the NMR tube, these are all the incorrect form of labeling. You just take your post-it and write your codes and just put it like this. It's not the correct way. So instead, you should label it and then round it with a parafilm or some tapes or something like this. So this is the correct way because you are putting it inside the probe. It goes inside. But when something is sticking out like this, so you cannot put it inside the probe. So the sampling technique, the labeling should be like this and not like this. This is the incorrect way, and this is the correct way of labeling the systems. So coming to the solvent solubility and quantity. So if the sample is not clear for any reason, such as poor solubility or turbidity, you'll be ending up with a poor spectrum. So a turbid solution always give a poor spectrum. You cannot have a good spectrum there. But if it is a clear solution, because we are talking about this liquid state NMR. So if it is a clear solution, you can have a good spectrum here. At the same time, a small amount of the solvent, you will end up with a bad spectrum because this is not enough. This solvent amount, which is shown here in this tube, is not enough to record a good spectrum. At the same time, if you go for a large amount of solvent, you can get a good spectrum, but you are wasting the solvent as well as money. So the exact amount needed is around 4 to 5 centimeter of filling up the tube with that solvent, whichever you need to record the NMR spectrum. So the sample depth should be 4.5 to 5 centimeter. Coming to the next, the cleanliness of NMR tubes. So there are certain do's and don'ts. So in the do's, make sure the NMR tube and the cap and anything else which is coming in contact with the sample is absolutely clean. For routine NMR, so if you have an NMR mission and if you have routine NMR samples are coming and you want to record NMRs, then this type of NMR tube washer is good. So an NMR tube washer with water and acetone. So you put your NMR tube here, just remove the cap from one end. So if this is the cap, remove the cap and put it on the other end. And then so that you can insert this. So you can insert this here. You can see you can insert this and it is attached to the vacuum, and you can pour acetone and water alternatively. And finally, you can clean up with acetone several times. So your NMR tube will be clean. You should not use the brush or abrasive cleaner. So that means the NMR tube will be damaged and it will reduce your spectral resolution. Similarly, after cleaning with your water and acetone, you can clean the NMR tube with cotton and wool stick. So regular cleaning is not always sufficient. So you can go for this type of cleaning. If the sample is very dilute, then the impurities may present there and it complicates the spectrum. In such cases, you can run a blank spectrum with a pure solvent, and then with the same batch of the solvent, you can record your samples. Sometimes the samples are very sensitive. If you take for biological samples, you will require sterile conditions, so that you have to put this sample in a vacuum, and then in oven, dry it, and then take away. If the tube is very dirty, then normal cleaning may not be sufficient. So you can put some cotton, wet the cotton with cotton wool with acetone, and then insert into the tube and clean. and then with a dry cotton until the tube is very clean. You can use this one also if you don't have the NMR tube washer for the cleanliness of NMR tubes. The next important factor is sample filtration. As I told, the sample should not be viscous, or it should not be turbid or opaque or something like suspensions. It should be very clear, transparent. So it is very important that the solution to be free of precipitate, dirt, fibers, etc. It should be very clean. So this can be achieved by filtering the sample. So you take a little more. You need 4.5 to 5 centimeter of the sample in the tube. So you can take around 8 or 7 that centimeter of level of solvent, or in ml you can take 1 or 2 ml more, and then you can take a pasture pipette. This is what a pasture pipette, put a cotton inside, and you can put the solvent inside so that all your precipitate which is formed, or the dirt or the fibers, will be filtered off, and you will be getting a clear liquid, clear sample. So filter the solution into the NMR tube directly using a teat, and if necessary you can force. So it is, the teat is nothing but like a nipple, right? So which can suck. So through that way you can take all the solvents and then put inside the NMR sample, NMR tube, and then you can go for recording. So this is more important, this filtration, because you should make sure that there should be no dirt or colloidal particles or suspension should be there. And then preventing the contamination from the cap. Okay, so because you can wash this stuff also, but many times we are so careless that we'll never wash the tube, because we always hold the NMR tube like this. We never invert. But at sometimes, without knowing this, even myself, I have taken the NMR sample in my pocket and went. So unknowingly, what happens? We just turn it out, sometimes slanting. So what happens? The sample comes to this edge, and it takes away all the material which is there in this cap. So we should make clear that there is nothing there in the cap also. For that, the tube cap may contaminate the sample. So even a new cap releases certain materials because it is absolutely plastic and polymer. So even the solvent can take some materials from the cap. So to prevent, close the tab with Teflon tape like this, and then close the NMR tube. So you can get a clear spectrum. So do not invert the tube. If this is the cap, in this pencil, if this is the cap, you should not invert at any cost. It should be like this. And if the solution is more viscous than water, more time is needed, more scanning time is needed for recording the spectra. Alternatively, we can use a special Teflon tube cap. Sometimes they use parafilm, maybe wrapped up at the top if you do not have the Teflon. So this contamination from the cap is very, very important in the sampling process. The next one is, say, you can see this is the small difference I've seen. The lower one is closed with Teflon. You can see how clean the spectra is, except the solvent peaks. Maybe I think this is the CDCl3 peaks with the HOD peak here. So it is very clean here. But at the same time, you can see this blue color peak, the upper one, which is without Teflon tape after inversion for 1/4 hour, like 15 minutes, inverted sample, you can see how the NMR spectra arises. So the cap purification is very, very important. So the use of Teflon and not inverting usually reduces the contamination by a factor of around 200. Then coming to the next part, if you have air sensitive and high pressure samples, what are you going to do? So you should create an inert atmosphere or vacuum is required for this type of sample, which is air sensitive. And if you want to measure the relaxation, T1 to T2, as Professor Emmanuel discussed in the previous section, T1, T2 relaxation measurement is desired. So you need to have an inert atmosphere or a vacuum here. If NOE, nuclear overacid effect, is being sought, then using an inert atmosphere increases the sensitivity of that NMR. So oxygen in air is paramagnetic, so it reduces the relaxation times. So you need to remove that oxygen in some cases. So you need to have an inert atmosphere there. So like organ atmosphere. So for that, some special NMR tubes are commercially available for sealing the samples. So see like this, you can have a constriction here so that a little amount is passed, either this type of NMR tubes, or you can have a sealed tube for which low pressure in an NMR tube. This will be put inside the NMR tube, wherein you have a piece of tissue paper here, or a piece of tissue, or something you can put inside, which will be resting. The seal tube will be containing the sample, will be resting on this. So like that, you can handle the air sensitive and high pressurized samples. So that is available in Wilmad 528 JY tubes. Coming to the solid state NMR samples, as usual, you grind the sample, the solid samples, with the help of a mortar and pestle like this. So you grind the sample with a pestle and mortar. And then place the rotor in its stand and put the powder in stages with a small spatula. You take up this, putting the sample in its stand and putting the powder into the rotor, and then compress it with the help of a compressor. From the top, you compress it, fill the rotor in the cap's place. What is this rotor? So the tube used for magic angle spinning, MAS, is small and white, and that is called as a rotor. This is what called as a rotor. Special tubes for magic angle spinning. So there are three main types, usually for solids, full 80 microliter and 50 microliter and 12 microliter. For semi-solids, 50 and 12 and 80 for complete solids. So these rotors and their accessories for solid state NMR, they are generally very, very expensive. There are special inserts used for these type, that is 12 and 50 microliter rotors. They are made from two materials, one from Teflon, that is white color. So this is the Teflon oriented. This one is the white color, which is Teflon oriented, these things. And the other one is KELF, which is transparent. If the sample is highly diamagnetic, like water chloroform, then Teflon is used, like this type. If it is less diamagnetic, like alcohol, DMSO, or acetone, then you can use KELF cap. The inserts are designed for use with liquid or soft samples. Now, you know the techniques, what you do, how to have the sample. Now, the quantity of your sample, how much you need. For proton NMR, for small organic compounds, the molecular weight up to 500. So anything between 1 to 20 milligram of the sample will be fine. But if you take concentrated solutions, is needed for, concentrated solutions can be viscous, and that leads to a broad signals. So generally that should be avoided. It should be clear liquid, and very dilute samples generally give many impurities and solvent peaks, because those peaks will come top. Your sample will be very less. So it should be appropriate. The concentration should be appropriate so that the quantity you take, like 1 to 20 milligram of the sample, will be fine for your proton NMR. Coming to the carbon-13, is present approximately in 1.1% natural abundance. That is approximately 6,000 times when you compare to proton NMR. So in this case, you should need at least 50 to 100 milligrams or more is generally fine for carbon-13. It is not like that you need 50 to 100 milligrams for carbon. Even with 5 to 10 milligrams, you can record carbon-13, but you need more time. The scanning time will be more. So preparing two samples, one dilute for proton NMR and one concentrated for carbon NMR is general practice, everybody. So in the daytime, for within 10 minutes, not even 10 minutes, 5 minutes, they record the proton and the same sample, or they concentrate that and overnight they run for the C13 NMR. But that is generally unnecessary practice. But if you have this much, you can 1 to 20 milligrams for proton NMR and 50 to 100 milligrams. So you can, within 1 hour, you can take the carbon-13 NMR spectrum. So in the sample preparation, as I told, 5 centimeter or 2 inches or 0.5 ml of the solvent is required for liquid state. So samples with too much of solvent, as I told you, is both waste of money, time, and the solvent. And sometimes it may provide poor signal to noise ratio. But if you have very limited amount of sample, less than 1 milligram, then using less solvent is very nice. Even you can reduce it, so to 3 centimeter or something like that. But minimum height, you need at least 1 or 2 centimeters. Otherwise, you should have intensive shimming because the magnetic field drift away. So the molecules will be in different places. So you should have the shimming properly to bring in all the magnetic into alignment. So this NMR spectra recorded using degassed solvents usually give you better signal to noise ratio, since, as you know, O2 gas is paramagnetic. So in a nutshell, all these things, whatever I have told so far, in a slide, use clean and dry NMR tubes and caps. Tubes can be reused. Generally, caps should not. It should be a use and throw, but we use several times. So 0.5 ml solvent, CDCl3 or DMSO, D6, etc. is good. Proton NMR, at least you need 10 milligrams, and for carbon-13, you need 50 to 100 milligrams. And solvent height, minimum 2 inches or 5 centimeter. And how do you clean the tubes? Rinse solvent wherever you are using with acetone and water alternatively, and then dry it, vacuum. Even at low temperature, drying is always good. So this is what a clean, clear solution, and this is a good sample preparation. If you take this one, it is an opaque solution, so you don't get a good NMR here. And this, there is a precipitate here, so it's also considered as a bad sample. And if this is more concentrated, viscous or colloids or diffusion or suspension, then you don't get the, depending upon the concentration gradient, you don't get a good NMR, so it's also a bad sample preparation. If there are two phases, if you have a D2O and a chloroform mixed together, you'll be in two phases. That's also not a good sample preparation. And if the amount of the solvent is less, not enough solvent, that is also a bad sample preparation. So this is what an ideal sample preparation in an NMR tube. So these are all just what I mean is don'ts in preparing the sample preparations. So this is what I told about the shimming, so which improves the magnetic field homogeneity. Okay, so the magnetic field is drifting away, but when you do shimming, it will all be aligned, and these are all the samples. So each and every sample, if the magnetic field is not uniform within the sample, so molecules at different position will experience different magnetic strength. But at the same time, when you do shimming, everything is aligned, so you can get a good NMR. Otherwise, you'll be having broad, distorted, and even sometimes additional signals will be there. Coming to the solvents, a suitable solvent should meet the following requirements. That is, it should be chemically inert towards the sample and even the sample tube. That's what I told you. For boron NMR, you should go for the quartz tube and not the borosilicate tube, because that interferes there. So it should be chemically inert. It should have no NMR spectra by itself, or a very simple spectrum. If you take CdCl3, it should not give anything in principle, but it has some moisture content, so it gives different signals. Easily recovered by distillation. But if you want to recover the sample, you know, this taking NMR is a constructive process. It is not a destructive process. So in the constructive process, you can take back the sample. If the original sample is needed back, so the distillation process could be done. So such like that, you should choose your solvent. Best solvents of proton NMR is they contain no protons at all. Hence, give no proton NMR signal like CCl4, CS2, or you can go for deuterated things. So what do you mean by deuterated solvents? You replace the proton, the hydrogen, with deuterium, so that you remove all the proton signals. So you have CdCl3, D2O, DMSO, D6. So you have several other samples, even benzene, C6, D6, etc. But there are certain disadvantages in this deuterium solvents. They are a little bit expensive. They contain a small amount of hydrogen somehow. So surely you'll be having a small signal from the solvent. You can see in the NMR. And then a spectrum of the solvent, the blank spectrum should be always run regularly and whenever a new lot of solvent is used, to make sure you are comparing with it. Otherwise, it will be misguiding you. So solvents, when one or more hydrogen atom are substituted with deuterated, then they are called as deuterated solvents. Possibly there are three main reasons which I've compiled why deuterated solvents are used in nuclear magnetic resonance spectroscopy or NMR. The first one is to avoid swamping by the solvent signal. That means any ordinary proton containing solvent has huge solvent absorption. Swamping in English, collection of water, pouring of water to that. So here it is a huge solvent absorption that would dominate the NMR spectrum. So you don't get your sample spectra there. You'll be getting only the solvent peak there, sometimes in NMR. So that is due to this. So you need to have deuterated solvents. So most NMR spectra are therefore recorded in a deuterated solvent, because these deuterated atoms absorb at a completely different frequency, not at the regular proton frequency. That is one advantage. The second reason is to stabilize the magnetic field strength. I told you they drift away. They tend to drift away, these magnetic field strength. So you need to have in alignment. So this field strength of superconducting magnets generally tends to drift away slowly. But these modern NMR spectrometers measure the deuterium absorption of the solvent and adjust the field strength to keep the resonance frequency or the field strength always in a constant manner. So these modern equipments, but in older days, you have to do shimming a lot for this to bring into an alignment. As such, it should not drift away. And the third one is to accurately define the 0 ppm. So the difference between deuterium frequency and 0 ppm, that is the TMS, is well known and well defined. So to satisfy those who are doing research in NMR alone, they need rigorous demands of NMR-based research because that is their main tool. They want to analyze many things. To have high quality, high purity, and high enriched deuterated solvents are required to do such type of research works to find. So to accurately define 0 ppm, these type of things are used. So deuterated solvent must be meticulously purified and analyzed for the presence of water content and its protonated form so as to obtain a high purified and deuterium enriched solvents. These are some of the examples where the trace impurities you can see. For example, if you take CdCl3, so deuterium chloroform CdCl3, so you can see the impurity of CHCl3 chloroform peak around 7.26 ppm and the water absorption I told you. So the water absorption peak somewhere around 1.6 ppm H2O. These are all the impurities in the case of CdCl3. At the same time, in the CdCl3, you can see the CD2Cl2 contaminant. So that is here. It is 5.5. You can see this CD2Cl2 contaminant in CdCl3. The same CdCl3, you can see the contaminant of acetone here in 2.2. These are all the trace impurities. If you do not wash your NMR tube properly and dry properly, if you're not removing the acetone, then you'll be having this peak while recording your NMR sample, whether it is, in CdCl3. Even though it is CdCl3, you'll be having the acetone peak there. Make sure the acetone is completely removed in the NMR tube before you preparing the sample. So this is ethanol and water contaminants. You can see ethanol, generally, due to the splitting, CH3, CH2. So due to the splitting of, you will be getting a quartet and a triplet. So those things that quartet and triplet are found here. And of course, for water peak also. So if you do not clean your NMR tubes, these type of impurities will be available in your NMR spectra once recorded, or even if you open and keep, if you're not maintaining your CdCl3 solvent at that particular conditions, these things you may see in your NMR spectra. Still further, you can see CdCl3 with water contaminant, as I told here, 1.6, and CdCl3 with ether contaminant, CHT, diethyl ether. You can see its spectra here. So the impurity peaks. And for DMSO with water contaminant, so this is the impurity at 3.2 ppm. This is the impurity peak. And for D2O, this is the around 4.9, 4.7. You have the HOD, that is this proton peak, somewhere at 4.7. So these are all the trace impurities because of solvents which appear in your NMR spectra after recording. Fine. I hope I have given enough things about the sampling process and the solvent and the impurities, etc. Now let us move to the second half of today's talk, that is the chemical shift. So before entering into the chemical shift, you need to know certain things called as in NMR shielding and deshielding. Generally, all the protons in a molecule have resonance. All the protons do not have the same resonance at the same frequency. The protons are surrounded by electrons. So they have different electronic environments from one another. Each proton have different electronic environment depending upon the electron density surrounding the protons. That means they vary from one proton to another. So if this is one proton, this is one proton, its electron density is different, and this one's electron density is different. That means the protons are shielded by the electrons which surround them. So they protect as a shield. These electrons which surround that, they protect the protons. You can take in that manner. So they shield the protons. So when you apply, this is the proton, when you apply a magnetic field, B0, so these valence electrons surrounding the protons, they are caused to circulate the protons, okay? They will be circulating the protons. And this circulation is called a local diamagnetic current. So this local diamagnetic current, it induces another magnetic field there. That field generally opposes. If you apply like this, if the arrow goes like this, this is the applied magnetic field, because of the electrons surrounding the proton, it induces a magnetic field which opposes from the top to bottom like this. It opposes, sometimes reinforces also. So this is called as local diamagnetic current, or it is called as diamagnetic shielding, or it is diamagnetic anisotropy. As a result of this diamagnetic anisotropy, each proton in this molecule is shielded from the applied magnetic field. It depends upon the electron density that's surrounding it. Now, greater the electron density, greater will be the induced current to oppose the applied magnetic field. The counterfield of the nucleus then diminishes, because the net applied magnetic field that nucleus experiences will be very diminished, because it protects. As a result, the nucleus persists at a lower frequency. It also absorbs the radio frequency radiation at this lower frequency. So this is called as shielding effect. Why you need a reference compound? Each proton in a molecule, as I told, they are in different environment. So they have a slightly different amount of electronic shielding. Different proton have different electron shielding, so that they will be having slightly different resonance frequency. Not all are same. So these difference in frequency is very small. You need to measure it. So the resonance frequency of protons, for example, if you take chloromethane and fluoromethane, it is only 72 Hertz when you apply 1.41 Tesla. So it is very difficult to measure these exact frequencies to that precision between chloromethane and fluoromethane. So far, no attempt has been made to measure the exact resonance frequency of any proton. We'll come to that later. For that, you need a reference compound, always. If you have a reference compound, based on that reference compound, you can calculate that very easily. So a reference compound is placed in the solution of the substance to be measured. And the resonance frequency of each proton is measured based on that sample, based on that reference compound. So the frequency difference is measured directly comparing to that reference compound. Generally, the standard reference compound is your trimethylsilane. So this is what that TMS, trimethylsilane. Hope you understand the need for a reference compound now. So why this TMS? Why they have chosen this TMS? There are certain properties for this TMS. The protons, there are 12 protons here surrounded the silicon. There's all these 4 methyl groups, 3, 6, 9, and these 12 proton gives a sharp single peak. They are highly shielded and they give sharp single peak, and these protons are identical. All are same. That's what I told you. Each proton gives different resonance frequency, but here all these things are same. So they give sharp singlet peak. The protons are isolated from the peaks of interest. So whatever peaks you need, you can take separately for your samples, because this will be considered as 0 ppm. I will come to that later. So it would be a good reference, since it would mark at the one end of the range. So one end of the range for TMS, you put it as 0 ppm, so the others can be easily measured. As I told you previously, you cannot measure the frequency, which is almost similar towards if you take two things. It is highly soluble in organic liquids, and it can be easily removed from the samples by just distillation process. So it is a common practice to add this tetramethylsilane to the deuterated solvents or related compounds as an internal reference standard for proton NMR and C13 NMR, where the proton signal occurring will be at 0 ppm for both proton and C13. So the shift from the TMS for a given proton depends upon the strength of the applied magnetic field. So what you apply, 1.4 Tesla or 2.535 Tesla, etc. So in an applied field of 1.41 Tesla, the resonance of a proton is approximately 60 megahertz. But at the same time, when you apply 2.35 Tesla, the resonance appears approximately at 100 megahertz. Now you can easily calculate the ratio of the frequencies. It is same, whatever the megahertz is. That is 100 by 60 is 2.35 Tesla, by 1.4 Tesla, it is 5:3. So for a proton, the shift in heads from TMS is 5:3, larger in 100 megahertz range than in 60 megahertz range. If this is the case, it will be confusing for the workers trying to compare the data. As I told, fluoromethane and chloromethane, it is very, very narrow. So it is very tough for the workers to work in NMR data to interpret it. So you need some other new parameter, which is entirely independent of the applied magnetic field, whether it is 1.41 or 2.35, that applied, irrespective of the applied magnetic field, you need a new parameter. So here comes the new parameter, which is called as the field independent measure, called the chemical shift or delta. How it is obtained? By dividing the shift in hertz, that is, you have a reference compound. From the reference compound, what is the shift? In hertz, I mean, the frequency of a given proton by the frequency in megahertz, what you apply of the spectrometer with which the shift value is obtained. So that is called as your chemical shift or delta value. So the chemical shift delta is given by shift in hertz, the spectrometer frequency divided by the spectrometer frequency in megahertz. So the chemical shift in del, this unit expresses the amount by which a proton resonance is shifted from the TMS in ppm. So the values of delta for a given proton is always same, irrespective of the field applied, whether it is 60 megahertz or 100 megahertz or 300 or 500, it is immaterial. So at 60 megahertz instrument, the shift of the proton for methyl bromide is somewhere around 162 hertz. At the same time, from the TMS, at the same time, while at 100 megahertz instrument, the shift is around 270 hertz. But when you calculate 162 by 60 using this formula, shift in hertz by spectrometer frequency in megahertz, so 162 hertz by 60 or 270 by 100, it gives the peak for this proton, CH3 methyl proton, is 270. So whether it is 100 megahertz or 60 megahertz, or still you go for upward 200, 400, 500, or 700, you'll be getting the peak at 2.7 ppm for methyl protons in methyl bromide. So this NMR chemical shift, previously we were using another notation called tau. So that is an old scale. So the resonance of protons in TMS comes exactly at 0.0 ppm. An old scale of chemical shift, which is no longer used currently, is called tau, TAU scale. So on this scale, the resonance position of TMS was well defined to be 10. So if you want to convert the delta value to tau value, you merely subtract just. So tau is equal to 10 minus delta. But no longer this tau is used. In case if you need, you can easily recalculate it. You can get from delta values. So this is the direction of NMR scan. So the NMR spectrometer actually scans from high delta value. So this side is the high delta value up till 1520. From here, it starts scanning from the downfield towards the upfield towards 0 and then negative. So this is what, so this area is higher in energy, higher in frequency. So it is downfield and it is deshielded. And this area, if you go, it is upfield, shielded, and lower energy and lower in frequency. I'll come to that. So these are all the simplified correlation chart. You can see where you get your NMR spectra. For example, if you go for benzene, it's somewhere around 7 to 8. CHCl3, you know it is 7.26. If you go for an aldehyde, it is between 9 to 10. Or if it is an acid, it is 11 to 12 ppm. See all the other things we have shown here. It's a simplified correlation chart. Now coming to the other part, NMR signals. What you what you infer from this NMR signals. One thing is the number of signals shows how many different kinds of protons are present. As I previously told, each proton has different resonance. So you can easily come to know how many different types of protons are present in your sample or in your compound. And then the location of the signal shows whether those protons are shielded or deshielded. The third one, the intensity of the signal shows the number of protons of the type which is there. And then the signal splitting shows the number of protons on the adjacent atoms. So these four major parameters can be taken from the NMR signals. So there are two types. One is the equivalent hydrogens, and non-equivalent. So the hydrogens that have the same chemical environment. So you can see here, if you take acetone, this CH3, this CH3, they are equivalent in equivalent protons. They have equivalent protons. So all equivalent hydrogens, they have only one NMR signal. See here, this is, you have two types of protons here, HA and HB. Since there is an electronegative atom attached to this will give one type of signal and this will be giving another type of signals. You will be having two NMR signals. Here, this environment is different, this environment is different, and this environment is absolutely different. So you'll be having three types of hydrogen here and three NMR signals can be obtained. So these things, after recording your NMR spectra, you can come to the inference. So the number of NMR signal is equal to the number of different types of hydrogen in protons. So equivalent protons give the same NMR signal. So still more, you can see if you have the same chlorine, this is all these two in the same environment, you'll be having only one NMR signal. But here you can see this is different, this is different. So you'll be having three types of NMR. So HA, HB, and HC, all even though they are CH2 methylene protons, their environment, this environment, this environment, this environment is differ. So you'll be having three types of protons here, and you have three NMR signals. Similarly, for others, okay, so on and so forth, you'll be having many NMR signals. So this one is if the replacement of one hydrogen at a time in a separate models create enantiomers. If you take this compound particularly, if you replace this hydrogen by some other guest species, then you can end up in enantiomers, and these protons are called as enantiotopic. These protons have same chemical shift general. If this replacement of hydrogen in separate models create diastereomers, then the hydrogen are called as diastereotopic. The diastereotopic protons have different chemical shift entirely. So we have seen about the delta, the chemical shift. Now we shall see what are all the factors which affects the chemical shift. Majorly three, I have concised, though there are many, like we can split into intermolecular and intramolecular like that. So I have given three highlighted. Deshielding by electronegative atoms or elements. Anisotropic fields usually due to the pi bonded electrons in the molecule, and deshielding due to the hydrogen bonding. So before that, you need to know what you mean by shielding and deshielding. Just a brief again. So in the vicinity of the nucleus, if the magnetic field generated by circulating the electron, which decreases the electronic and external magnetic field that the proton feels. See here, this is a nucleus. This nucleus doesn't have any electrons here. This is an isolated proton. This is the applied magnetic field. That means this total field is felt by this nucleus. It is completely deshielded. There is no shielding process here. But if you take this proton here, it is circulated by electrons due to the induced magnetic field here. Sorry, applied magnetic field. When you apply the magnetic field, the electrons tend to circulate so that there is an induced magnetic field developed here, so which opposes this field. That means these electrons which circulate the nucleus shield the nucleus from the applied magnetic field. So that is which opposes this. That's what the arrow is down. That means the nucleus is shielded. See here, the same thing. So now when this nucleus is shielded, what happens? You have shift of this chemical, the chemical shift is towards upfield when it is shielded. That means the frequency will be lower, the energy will be lower because the energy difference is smaller. Okay, the energy difference, the nucleus fields, so a smaller resultant field. The energy difference is lower. So according to U, E is equal to h nu when the energy is proportional to the frequency. So energy is lower, the frequency is lower, so that the chemical, it is completely shifted towards the upfield. But at the same time, when it is deshielded, that means the nucleus feels a larger resultant field. So deshielded, what happens? You have a large magnetic field, which will be large in energy. So a higher frequency is absorbed, and you have a higher chemical shift or downfield shift. Right? So this you need to know between what you mean by shielding and deshielding. So coming to that, deshielding by an electronegative atom. So when you take this compound, so there is an electronegative atom attached here, so it assumes a partial negative charge, and this is a partial positive charge. So this chlorine abstracts all the electrons towards itself. So the electrons which are shielding this hydrogen is gone towards this side. So that means what? Deshielding takes place. When there is a deshielding, what happens? The protons are downfield. It goes to the lower field because the energy difference is lower and the frequency is lower. It will be downfield chemical shift from the TMS 0. See, this is the compound. These are some of the compounds, CH3X. So you have substituted with halogens, the alkyl halides, fluorine, and this is OH and chlorine, bromine, iodine, etc. And these are the electronegative elements are given here, and the electronegativity of those elements are given here. So this is the more or the most electronegative element, which is 4, its value. So now the chemical shift, it goes 4.26 because deshielding takes place to a larger extent, because electrons are pulled toward this side and there is no shielding of the proton takes place. So that the chemical shift is downfield, higher in energy, higher in frequency, because the induced field reinforces the applied field. So you have the higher energy. That's what you call deshielded. But shielded, the induced field opposes the applied field. So you get shielded. So here, if you have an electronegative atom, it deshields and shifts the chemical shift towards downfield. So when you have shielding part in the upfield, so the effect decreases with the increasing distance from the electronegative atom, as I shown here. The next one is the S character. So here, hybridization of a carbon atom plays a major role. So as the S character of the carbon atom increases, the electron cloud is held more closer to the carbon, so the deshielding of the proton takes place. So as you know, this carbon is sp3 and this is sp2 and this is sp. That means the electronegativity character of this S here in sp is more. So in principle, it should be having a lower frequency and lower energy, and it should be deshielded, and you'll be having a downfield chemical shift if you have an sp character. So this should be most downfield, and this is in the middle, and this should be in the upfield, right? So as the S character increases, it is downfield, and you'll be getting the higher delta value according to this reasoning. But what happens is, it is in the inverse way. You can see sp2 is downfield, and sp in the middle and sp3 is higher. So why? So I may leave for you to guess the answer, why it is. So we are talking about the electronegativity character. So as the electronegativity character increases, in principle, it should be downfield. So that this sp should be in the downfield. Then comes sp2 and then sp3, but it is in the reverse case. So there is one more point. The clue is the anisotropy. I'll come to that. So you can keep guessing for that. The second one is the anisotropic effects due to the presence of the pi bonds. So anisotropy refers to the dissimilar electron density, which is there in all directions. So the presence of a nearby pi bond or the pi system, this greatly affects the chemical shift there. How? We can take an example, the acetylenic protons. Just now I told you the sp character. So if you take this sp character in a magnetic field, so this is this green arrow, this is the magnetic field, applied magnetic field, which is B0 here. The pi electrons of the carbon-carbon triple bond are induced to circulate when you apply this applied field B0. They are induced to circulate. When they induce, what happens? They create an induced magnetic field. Either they oppose or they reinforce, both can happen. So you can see here, in this case, in acetylenic protons, when they circulate, when they induce this, what happens? It will go like this and it will be induced. This field will be operating like this. What happens? The induced magnetic field opposes. When it comes like this arrow and this arrow, you can see this is going top, this is coming down. So the secondary magnetic field or the induced magnetic field opposes to the applied magnetic field. When this opposing happening, what happens? You have a weaker magnetic field and a lower frequency, so that the chemical shift should be towards upfield. towards the TMS, 0. So that's the reason previous I told you, this case, this guy, actually this SP, this acetylenic comes in the middle, though the electronegativity of this is less than compared to sp2. So because of this reason, it's upfield shifted. So the nucleus is shielded here, and the absorption is upfield, right? Okay, because it's shielded, you have lower in energy, lower in frequency, and it is upfield shifted. When you take a vinyl protons, so this is what the vinyl protons here now it creates, when you have, this is the applied magnetic field B0. When you apply, the electrons tend to circulate, they create a magnetic field, induced magnetic field. So that magnetic field here reinforces. That means it adds to the applied magnetic field in the vicinity of these protons. So what happens? Now the proton feels a strong magnetic field, and they are in higher frequency. That means these protons are deshielded, and your chemical shift will be downfield. Another example, the ring current in benzene. So if you take this benzene, these protons are outside. So when you have the applied magnetic field B0 here, similarly, when you have given applied magnetic field, the pi electrons, 6 pi electrons inside the benzene ring above and below the plane, they circulate and they create an induced magnetic field, and that induced magnetic field reinforces, that is, adds to this. You can see here, this is also moving top, this is also moving top. They add together, so that what happens when they add up? That means deshielding of hydrogen takes place. The secondary magnetic field generated by circulating pi electrons deshields the aromatic proton. When it is deshields, it is downward shift. Always you have to correlate to certain things, and remember, DD correlation, that is always deshielding downfield. It's easy to remember, DD correlation. Okay, so that means deshielding downfield. If you remember this, you can easily, the other one is opposite, shielded upfield. So why it is deshielding? Because there is higher energy, higher magnetic field, and then higher frequency is there. The third factor is the hydrogen bonding. Here also the deshielding takes place, because when there is an electronegative atom attached, you have the hydrogen bonding between the electronegative atom and the hydrogen atom. So this electronegative atom because of this hydrogen bonding, it lengthens the OH bond and reduce the valence electron density around the proton. When it reduces, what happens? Automatically deshielding takes place, and it shifted towards the downfield in the NMR spectrum. So it depends upon how much hydrogen bonding taking place. Here we have inter and intra, so that takes a longer. So I have just confined into small, just hydrogen bonding, which is deshielding. So if you take an alcohol, you can see here, this is an alcohol. Alcohols vary in chemical shift from 0.5 to 5, depending upon the hydrogen bonding. If you take an acid here, you can see it forms a good 6-membered ring. Strong hydrogen bonding forms dimers. So it is shifted, the deshielding happens, and it shifted towards the downfield around 10 to 12 ppm. But if you take this one, you have an internal hydrogen bonding. That is intramolecular hydrogen bonding, and that too, it's very specific, which is called as RAHB, that is resonance assisted hydrogen bonding. If you have this type of resonance assisted hydrogen bonding, you can see the delta value is still far. That is downfielded to the extreme, nearly 14, you can see, because of this resonance assisted hydrogen bonding here. So this is the protons in a given environment. They absorb in a predictable region in an NMR spectrum. I have shown this already. Correlation spectra, where in which region, what type of NMR spectra you can get it. Okay, this is about that. Do we have, because we have a reference compound like 0 for TMS, 0 ppm. So do we have anything negative, -1, -2? The answer is yes. This particular slide I've just taken from the Wikipedia. Negative HNMR shifts do exist. For example, inner nitrogen bound protons of porphyrin molecules. They usually have the negative chemical shifts. That is ranging from -1.5 to -4.5 ppm due to the strong shielding effect of macrocyclic aromatic ring on the protons inside the macrocycle. as opposed to the protons outside the circle. So if you take these type of porphyrin rings, if you take this is a ring system, there are certain protons inside the system, there are certain protons outside the system. So outside the system have different experience with the magnetic field. Inside protons have different experience with the magnetic field. As I told, either they reinforce or they oppose. So if your compound is more shielded than the TMS, because whenever there is shielding takes place, it moves towards the upfield. But if it is more shielded than the TMS, then it goes beyond the TMS, then you get this type of negative. But if it happens as you, if your sample is not like that, and if you have a negative value, then you have to recalibrate your instrument. We should make sure. So if you take this benzene, I told you H is projected outside, so it is outside chemical shift. So that is what happens, higher energy, it actually reinforces, you get the downfield. But if you take this aniline ring, so certain protons are inside and certain protons are outside. See, the protons which are outside, they align with the induced magnetic field, that is they reinforce, you get a larger magnetic field, and then you have larger frequency and larger energy, and they are downfield shift. They are deshielded and downfield. You can see here for this HA proton, it is somewhere around 8.9. But at the same time, the protons which are inner, which is inside this ring, here, you know, it goes here. So the field comes like this and goes inside. So it actually opposes this applied magnetic field. Outside reinforces, but inside opposes. When it opposes and when such a strong shielding takes place, which overcomes the TMS, that means you get a negative chemical shift. So it opposes, so you get a negative chemical shift here in the case of this molecule. You can have some examples. You can see here this particular. So induced field by circulating electrons is opposed to the applied electron field. So this is nothing but your Lenz's law. Generally, the pi bonds are not usually able to circulate freely, so that the chemical shift will depend upon the orientation of the nucleus, how they are with respect to the bond they are formed, triple bond and double bond or pi delocalization, etc. As a result, higher frequency chemical shifts can be obtained for the protons outside the ring, and lower frequency shifts can be obtained inside the ring due to the opposition outside and due to the reinforcement inside. Sorry, I mean opposes inside and reinforces outside. So you can see here this one, this methyl group, these two methyl groups which are inside, they give a chemical shift in minus 3.88 and minus 3.91. Whereas this tertiary butyl group, which is outside, they are around 1.53 and 1.55. So this gives negative resonance and this gives the positive resonance. There is some other thing called as shift reagents. So these are agents used to cause shift in the NMR spectrum. I mean the chemical shift. So the amount of shift depends upon the distance between the shift reagent and the proton, and the concentration of the shift reagent you are using it. So the advantages of using the shift reagents are, it gives a spectra which are much easier to interpret because it will not interfere. No chemical manipulation of the sample is needed because it will be different. I mean, you can easily analyze, because if it is crowded in one area, this shift gives to the other areas, so you can easily check your NMR and interpret it very cleanly, and it is more easily obtained. So paramagnetic materials can cause chemical shifts, for example, lanthanides. The complexes of europium, erbium, thallium, ytterbium, they shift the resonance towards the lower field, I mean upfield. Complexes of cerium, neodymium, and terbium shift resonance towards the higher field or the downfield shifts. This is an example. So this guy, tris dipivalyl methanato europium 3, this is a good shift reagent which reduces the shielding. That means goes for deshielding, downfield shift. You can see this. With no shift, you have the NMR spectra for 2-methyl-3-pentanol. All its peaks are here. But when you have europium, this complex with 0.05 mole percent, it is shifted here. When you increase, when it is 0.9, it has shifted to 8. Where it was 1 or 2, it is shifted to 8, and splitting pattern is very fine when you compare here. So you can easily interpret the NMR, what peaks it is. Similarly, you can see here, so from here, it has been shifted to here when you use 1 mole% of the europium complex with for 2-methyl-3-pentanol, just an example for shift reagents. Thank you. I have covered up the sampling process and the chemical shift today. Thank you for the opportunity. You'll be continued with equivalent H splitting and